Alright, today I'll be using Rust. It's the future of systems programming, and it's one of the main competition to languages such as C and C++. But I have some extensive knowledge in C, and I do have some, intermediate knowledge with C++. So I've already been using this language for a week now, and I will do the stuff that I do in every new programming language that I learn, and that is to create a data structure. And of course, we'll write one of the oldest data structure in the book, a doubly linked list. Now, I know that there is this having a self-referential, I don't know how to say that, a data structure that references itself. Having that is actually pretty complicated, especially in Rust, because Rust has a lot of memory safety features, and one of that is a borrow checker that ensures you don't have data erased and other memory related issue. And so it doesn't really go that well with it, but this is what I do in every language. And I've wrote a lot of other small stuff in Rust, and so far, I mean, it's giving a good case for a language, and I feel like it will probably be adopted pretty soon, especially because I worked in a lot of different languages in the past, C#, Java, Kotlin, and it looks like a modern language for systems programming, something that we needed for a long time, especially if you're working in C and you have to deal with their build tools there, and C is so old that we still have to it's the compiler reads code from top to bottom, so you have to there's a lot of like old stuff that we've gone through, so Rust will be a good language. Anyway, there's probably a billion of videos in the internet that explains why Rust is the future. I don't want to explain that. I just want to write a linked list, a doubly linked list in Rust. So there are 3 ways that I know of to write this. So I'll first of all go with my C approach, where it's just, it's not the best way to write a linked list. So first of all, I'm going to create a new file, and I'm just going to call it unsafe linked list, because it will be using a lot of unsaved stuff. And in Rust, unsafe pretty much means you're going to be working with pointers directly. You're going to be writing in pointers, and it could have segmentation fault, which is a nightmare. Anyway, so and then I'm going to also use that as a module, and then probably use that and it's probably going to be called linked list. They're all going to be called linked list. And so the first things first, obviously Rust also has generic, so we'll probably want to make it as generic as possible. So yeah, so let's just start type aliasing. It's the same type aliasing, like it's a type def but in Rust, and using statement in C++. And because I don't like to see naked pointers a lot, so yep. So first of all, we have to actually create the list. So I mean, if you have a singly linked list, you can just use a node. You just need one structure node, but we need both the head and the tail. So they're both mutable pointers, and mutable just means that you can reassign the pointers. And of course we need the node, and the node itself is gonna have some kind of content, and I can make it generic. Should I? I could probably make it generic, but generic has some weird rules. Like generic works with traits, which is like some kind of like it's like an interface, but with metaprogramming. So yeah, I'll just make it so it holds, normal numbers. So I32, that's 32-bit integer, assigned, and then obviously we need the node pointer to next and previous. Nothing special. This is pretty much like C, the different syntax so far. But this language is nothing like C. It's more comparable to C++ than C. So never make the mistake thinking that this is like C. So we're gonna have the implementation of this doubly linked list, which just means it creates associative functions and methods. Well, C doesn't have methods, so it's basically like a static one, like C++ namespace, and then obviously also methods. This is not a Rust tutorial, so this is just me jamming, writing a linked list. And if you really need to read Rust somewhere, their official book is pretty good. That's where I learned pretty much all of it. And they also have a self-documentation. So this is how you create function. It's public. Start new. It's like a constructor. And we gonna return a instance of DoublyLinkedList. And obviously by default, DoublyLinkedList is gonna have a null pointer, which, this is how you do a null mutable pointer. And I got cline, which auto imports stuff for me, which is nice. And both tail and head will be null pointers, so they don't point at anything. It's just an empty structure by default. So obviously one of the first things we want to do is we want to push back, or just, we want to add something to the tail. And if there's no tail or head, we create a tail or head. So, since it's a method and not a static function, we need a reference to the self. It has to be mutable because we want to change it. And of course the value we want to push. So yeah, so that's the first thing. So now, obviously Rust doesn't have malloc. It doesn't have any integrated allocation. So every allocation goes through a box, pretty much is what they call. So we are gonna create memory on the heap by doing box.new, and obviously that data will be a node with the value. I don't think we did. I'm gonna define that in a second. And node new, and then obviously it returns a box. We don't want a box because we're in C land in a way. This is obviously not the right way to do this, but we're trying to do it in the C world, so we somehow need to get a pointer of that. So I believe as mute, so now we get a mutable reference to the data inside, and then a reference is like a sugar-coated pointer, but compiler treats them special. So this is a casting to a node pointer. And then we obviously want to do our code. So we want to see if there's no tail. Okay, then that means there's no head. Can have a tail with a head without a head. So we set the pointers of head and tail to the node. And so far you're like, okay, we didn't need to use the unsafe keyword. So the only time you can still play with pointers in a safe environment, but whenever you want to dereference a pointer, it has to be in an unsafe place. So if there's a self, then we want to append it to the self, pretty much. So now we have to go to the unsafe land. This is a land you don't want to go a lot, but as a game developer, right now you still have to use unsafe code, but eventually you probably won't need to. So first we'll dereference the tail and then send the next of the tail to this new node, because the new node will be the tail. And then we want the previous for the new node to be the old tail. And then we want the tail to be the new node. Okay, so it gives you, if you hover over it, it gives you like a color. It's like, you probably don't want to do this because now we're outside of the memory safety features that Rust guarantees us, which is not a good land to be in. So then we just want to print this. Obviously this is not, I'm not gonna spend, this is gonna be too long if I just create every stuff that a linked list does. This is just bare bones. So we're gonna go from head pointer, we're gonna loop. This is a nice thing. It's like a this like for this while true. It's like an infinite loop. If the current node is null, then we break. Oh, I keep forgetting we don't need the parentheses. Thanks for telling me. Clippy or cargo check, whatever one you want to use. Alright, so if it's not null, and now we're gonna dereference it because we want to print the value. So value, I'm gonna dereference the current node and get the content. And then we want to go to the next one. That's pretty much the fastest way to write, a node. And obviously we haven't created the new. Why is it not giving me an error? I didn't create this. Something not right? Yeah, see, the ID integration is not really that great. So obviously I need to implement the new for the node. And it'll take a element and it will return a node, and that node will be with the same content. Next will be null, no next, no previous. So yeah, that's pretty much your basic. If you're very much into C and you just testing this language and you just know the basics, you'll probably write something like this. And obviously if you learned about the unsafe keyword. But if you're using Rust like this, might as well just use C, man, because you're not getting anything out of it. Well, you do get cargo, which is pretty cool. It's like one of the best packaging software and build software. It does both. And you can also use makefiles with it. And you're also getting not having to, the compiler doesn't read code from top to bottom, which is pretty good. Anyway, so let's just use that linked list, list. Well, actually, I need to get rid of my C syntax. Didn't I just include you? Why do I need to? Oh no, that's the wrong linked list. I probably should call this something else, like list, because I'm clashing names with Rust's original stuff. And obviously we need to make it mutable so we can modify, so we can get a self. Is that list is also being used for something? What is happening? Oh, I call it DoublyLinkedList. No wonder. Why did I do this? Alright. And so it's DoublyLinkedList. I'm not getting any error checking. Oh, I know why. So if you're in C-Line, one of the first thing you want to do is not that. You want to use Rust format, and you want to get Clippy and run it in Fly. That makes things so much easier. Alright, so let's just put 25, just This is probably going to be a long video. And then we just print that and we run it, cargo run, and then we get 25, 50, 75. So that's probably not the way you want to use Rust. Now, one of the first thing when you look up, you know, obviously linked list is it's not a good data structure to use nowadays, because, you know, you get all sorts of problems like missing cache lines, and, you know, it's just not performing. And every time you want to iterate, you got to go through a, you know, pointer dereference. You know, it's not good. Storage is also bad. Actually, yeah. The only good reason, well, back in the day was, you know, it doesn't take a lot of storage, and you could just do insertion very quickly, and you don't have to go through the whole, you know, reallocation when your size grows. Anyway, we don't want to do that. We want to write Rust, and then if you look at, you know, another implementation, it's just gonna be like a stack type linked list. It's like stack linked list, I think. So this is like one of the other way, which uses a lot of powerful features of Rust, and you can get cache cohesion if your, you know, list is ordered. So it's probably another way to use a linked list, but this is also not the best way, but I want to show it. So mod stack linked list. I'll just let CLine do the use for me. Anyway, so let's just make this, you know, generic, because that was boring to not have generics. So, you know, your node. So this time, whatever I'm currently doing is already interesting, and I'll explain in a second. You're like, what the hell is this? Yeah, it's kind of weird. So first things first, and obviously, no, okay. So it's generics. Rust has generics. It works like, you know, it's a mixture of C# and C++, C++ concepts. Not as powerful as C++ concepts, and C# just, you know, having, you know, generics be more than a copy paste. It has actual type safety. Anyway, so there's next and previous, and they have an option of an index. So obviously, you know, at this point we're gonna be working with vectors or dynamic arrays, which is going to be interesting, and I'll show you how. So this also has its own problems, which I'll explain later. So let's just create a generic implementation for node, which will take a generic value, and this self keyword, which just means this gets, you know, here. It's like the same as the type that's being implemented. And we have the node element will be value, next will be none, previous will be none. So this will be a little bit, you know, slow, or not slow in the sense of this is the fastest performing linked list there, if you're just talking about search and, you know, iteration. But it's slow to write this, because it's like it's very complicated. Well, not complicated, it's just, you'll see. So now we're gonna need Arraylist. Why am I? Well, it is an Arraylist, but okay, why not? We'll just call it Arraylist. It's a type of linked list. So we need a head, which is gonna be usize, and tail. Usize. So everything is index space in this, you know, in this data structure. So obviously you can tell that there's not going to be a lot of pointers. Actually, it's not going to be any pointers in this implementation. So which means obviously we need a place to store this. So we have a storage vector, which is a dynamic storage, dynamic array on the heap. Yeah. And obviously it's going to store generic node. Okay. Now we want to do an implementation for this. And we want to only do this if t is a copy, because we want to copy these values inside the vec. And because vec also needs to grow, so I think it needs copy, or maybe move. I don't know. C++, you know, had a restriction where every vector items has to be copied, or has to have been copyable. So I don't know if that's the case in Rust. Alright, so we create a new... Okay, what the hell? No. Alright. My ID is going nuts. Alright, so head will be none. This is a good thing with option. Option is just a better way to do null pointers in Rust, because it just means that it either has a value, and if it has, it's going to return the value, or it's going to be none. It's like an enum, but a powerful enum, like a variant in C++, or similar to union. But you know, enum, it's based on the largest size. So, you know, and obviously I'm still new to, you know, Rust. I've only been learning this like 7-8 days. So, all right, we create a new storage, and now we're gonna create our classic pushback that adds an item to the end of the tail. It's really hard to talk and type. Alright, so now this will tell us what the size is. What the index is of the item we're gonna add. Because it's 1 off. Because if you have 5 elements, the last element is 4th one, but this will give you 5 because we're gonna add an element. So once we push this, now this new node you know, has this index. So yeah, so now we created a node already, and now we're gonna match it on the self.tail because it's an option. So if the tail, let's let the ID create this stuff. So if there's nothing on the tail, it's an easy thing. Just put the head to the index of the new node and the tail to the index of the new node. And if there's some, then we want to get the tail index of that sum, and then we want to obviously get the tail, and we want to get the mutable reference of the element in the tail. So that will give me the node, and because node has information of what the next and the previous is, and so we want to set the next for this tail to be the new tail, which is gonna be the index of the new node. And then we get the new node, which is gonna be like that, and then we set the previous to be the index of the tail, so tail index, and obviously it will be a sum, and then self.tail, the new tail will be the new index. Okay. So already you can tell that this is kind of, you know, yeah, it's involved, let's just say that. And I want to implement a little bit more functionality into this, just so I can show you how it works, because this is not it's not a really, I don't even know if this is a linked list, but this is some kind of data structure that represents some of the functionality of a linked list. So I'll show you how you can implement this, because I don't know. I don't think anyone has done something so weird and bizarre. So obviously we want to get the tail, and if the option is none, then return. That's the question mark. And then we get the storage, get the tail index, we get the element. That's just a peek. This peek is very, easy, and if you want to get peek front, it will be the head instead of the tail. We should call it the index, because then I don't have to change it so much. Alright. So that's the peek, but then you're going to be thinking, okay, what if I want to insert, an item next to another item? Because obviously you can tell that the indexes are weird. So we have this indexes in the storage which doesn't match the indexes on how it will be represented in the actual, to whatever is consuming this list. So I can show you better. So let me show you. So if I do like an iteration, and this time I want to do a collect, because Rust loves this collect thing where it's like it turns one data structure to another. So we'll turn this into a vec. And I don't want to implement traits, so yeah. So you get the current index, and that's the index of the storage index. All right, and then obviously you want to have a vec that you want to return, and then you want to return that vec, and then you want to do a loop match current index, add that, none, break, because we have nothing, and if there is an index, we want to get the node from the index, and then we want to push this value for the node, current index, go to the next one. So what you'll find is we are not using the indexes of the storage itself to iterate. We're actually using the indexes marked in the data itself, like the next and the previous, which is useful in linked list if you really want because a lot of time DQ, I don't know how you say that, is implemented in a way where the ordering matters. So you could still matter an order that's not just which one you push first, but you can really, you could do this, in with a normal array, which is why this is not the best thing to showcase, but you could be able to do it with less reallocation. Because if you want to insert something in the middle, the actual array is still in the array. It's going to be inserted in the end, not in the middle. It's just we're using the indexes to actually iterate. So this will collect, and then we're talking about the insert, so let's just add the insert. It's where things gets a little bit crazy, so I might have to speed code this because it's kind of involved. So obviously we need a new physical index, which is gonna be the one that we're gonna add right now. Value, and then we also need the next physical index so we can have a reference. You'll see why it's needed, and it starts from the head. And then a logical index. This is the index that the user believes that the data is stored in, but it's not, because the data implemented using a vector. So they matter. All of this matters. So we're gonna go to next physical address. And if there is none, then we break, or actually return in this case, because it's a function that does nothing else afterwards. A physical index. So now we have some sort of data, physical index. So now we want to get the node, because we want to keep iterating until the logical index matches with the logical index the user is asked for, because we want to insert after that logical index. So storage, physical index. Next physical index will be node.next. So that's the next physical address index, because next gives us a physical index. It's confusing. So now if the logical index matches with the index that the user is asking for the item to be inserted afterwards, then we can do the insertion. Now this is where things gets a little bit crazy. Obviously we want to return, and so we get the node that is the current physical address, or the one in the current physical index. I mean, not address. We're not going to be dealing with address here. So this is the physical index where we want to insert an item after this index. So we need to change, and we also want to know what the old next item was for this node. So we will cache it. And then, oops, I don't want to do that. Let me think. Yeah. Okay. So then obviously we do node.next, to be this new physical address. So because it will be after this one. And then we need to, get the new node, the one that we're inserting, and obviously want to have it mutable reference, which with new physical index. And then, that new node previous will be this node, which will be some the physical index, which is this node, actual physical address. And now we can see if there has been an old index, and we get the old index if there is, or the old next index. Then we want to also get the old next node, because we want to add it to the previous, or the previous needs to be the new one, so because it sits right between these two. What is wrong? Oh, yeah. And then old next node previous will be this new physical index, and then this new node, because so if I don't redo this again, I'll run into borrow checker issue, because this old next, because they're both using the same array, so there's some stuff that I know it's safe, but borrow checker doesn't seem to think so. So I'll need to re-get this just so I can do the next for this to be that old next. Whew. And then finally, every time we loop and we want to increase the logical index, just like that. And then I'll just get some of the test. And obviously when I was working on it, I called it Arraylist. It's called Arraylist. Stack linked list. Yep. So what's wrong? Pink front, peak front. I thought I added that. Oh, misspelled it. Yep. So, and then you can do the test, and I didn't implement that. Yeah, I went hard on this one for some reason. It was fun. It was weird. Yep. So test finish. It was all successful. So yeah, here I tested the insert. I have this, so I have 25, 50, 75, 100 because it's pushed back, which means it's, a stack pretty much. So this is going to be 100, or yeah. So this is what it's expecting, and I put 35 in between 50 and 75, and it works. Yeah, so that is another way of doing a weird version of linked list, where you get some of the functionality of a linked list, but use some kind of array internally. And that's actually how graphs are done, and a lot of other things and it gets weird when you gonna remove it a lot and add a lot, which is why I have the third solution, which is, gonna be using a lot of Rust features. Let's just say that. So if you don't know Rust, you'll be confused, which is okay. It's okay to be confused. I was. So this is how I think most people will implement self-referential data structure. I said it right this time. All right. So yeah. Oh, I forgot I had this. All right. So DoublyLinkedList. How would you implement this the Rust way? Such a long video. Jeez, I'm sorry if you are still watching this. So obviously we're gonna need a DoublyLinkedList struct, and your head, your tail. But we're gonna use Rust features, so obviously it's an option because there's a chance there could be no head or tail. And now, this is kind of how you would implement it in C++. So DoublyLinkedList, in a way, that we have to think about ownership in here. And so who owns the head? Well, let's just think, the head can be only owned by head. But, the tail could own the head in a way. So we'll use something called RC, which just stands for reference counting. So it's a shared pointer pretty much. So, and this is how Java garbage collection works in runtime, where it's just, whenever there's the ref count is 0, then just deallocate the object. This is how it works. So this means that whatever I put inside, whatever type I put inside, that value will be owned by multiple, or that resource will be owned by multiple owners. So we obviously want it to be a node, right? But there's a problem with this. Let's just add node now. Oops, I missed a comma. So node, I'll just use i32 generics. It's overrated. No, I'm just joking. And obviously next will always also need, because next also needs to own what the value is next, because linked list basically works this way, right? I don't know why I'm doing this. Everyone should know this. Okay, so it works this way. So you have 1, then you add, you push something in the tail, so then you get 1, and then 1, but that 1, and then you want to push 2, so it's like this. So if there's no 1, there's no 2. And if you want to add 3, I'll just do it this way. So 1, and now you have 1, 2, or 2, and then you want to add 3, and then you want to add 4. It's kind of like a diagonal. It's not really anytime I see a linked list, it's shows that as like this. It it's not like this. It's kind of, I mean, yeah, you feel like they're linked together, but they're not really linked together. Like 4 is linked to 1 in a way. So if there's no 4, then there is no 2, 3, and 4. So obviously next needs to own the node. So that's why, and it has to be shared amongst, if it's like head or tail, or if the next is a tail, then there's 2 owners, so we need to share that. But this previous, if we have previous also owning, you know, the resource, then we're gonna have a memory leak, because the ref count will never be 0, because they're both owning each other. So who owns who? No one knows. So we probably want a weak pointer. So it's just it's like owning, it's just having a view to the owner, or just borrowing in a way. You know, it's the same weak pointer in C++, where you don't increase the ref count every time you get the resource. So, you know, even if there's like a weak reference to a resource, that weak reference is not going to keep the resource alive. Alright, so this is not bad, but this won't work. Now, the thing with RC and weak is that whatever is inside is immutable. Yes, you can make you can create a new refresh counting, but we want to mutate what's inside, right? We want to change the next and the previous pointer, but you can't do that. You can't mutate, you know, because a threat, it's threat safe to keep this immutable. So Rust has something called interior mutability, which makes it so that on the surface it's immutable, but implementation wise you can, you know, have scopes that makes the value that's contained within that mutable. And you do that with something called ref cell, which is a reference counted cell, and in cell just means it's something that can be mutated. Now it's reference counted because it still respects the ownership rules for Rust, but in runtime instead of compile time. So this is why we use ref cell. So because we want to modify the node, and we want to do the same thing for next and previous, because we want to modify this. Yep, that's a lot of brackets. Yes, I hear you. Oh, that should not be like this, because we don't want to change the reference of the weak pointer, only the value containing inside. Alright, now we can actually start implementing stuff. And this video has been going on a lot. I'm sorry, this is not a tutorial. If you're expecting a tutorial, it's not it. And I doubt anyone will be watching this anyway. So I'll just do it at my own pace, because I got actual stuff to do. It's a weekend, man. I don't want to be coding so much. Alright, so we create the new. You've seen it a billion times. Not billion, like 3 times, but. And we get our classical pushback with the value. And obviously we create the node, but we don't actually put it inside any reference, any smart pointers. It's just the value created in the stack. Now you probably want to, if the value is big, but it's an int32, so I can create it on the stack. It's fine. I haven't created new for this. Oh, come on. Element. What am I? Yeah. Sometimes it's hard to context switch when I program in like C, C++, and Kotlin and Java and C#. So sometimes I use the wrong stuff for each language. It's okay. Everyone can feel this pain. Let's just have less programming language, please. We don't need so many. Alright. So, obviously now we need to... Well, we can actually put it inside yet, because obviously we don't want to put it inside the head. There's a pushback, not a push front. So we want to see we want to get a reference of the value inside the tail. If there's no tail, then we want to create a tail and a head. So then we get the node back, and obviously now we have to actually put it inside a smart pointer. That way we can, assign the head. And now we can't just do node, because that moves ownership. And this is the difference between C++ and Rust. You don't... Yeah, it's moved by default, not copy. So you want to copy the ownership. And you do that using, let's pretty much clone. And then you get the reference of the thing you want to clone. And you do the same with this. And then obviously this scope, this will, deduct a reference count because the scope ends, but it'll be alive due to the head and tail. So we're good. And then obviously if there's a tail that already exists, then we want to get the new node's previous and set it to the tail of this old tail. So we need a weak counter and a weak reference. To get a weak pointer or a weak reference, you do downgrade and then the node. Okay, so that will give me a weak reference to the previous tail, and then we want to create data for the smart. We want to create the wrapper, pointer wrapper. I mean, there's so much terms for all this crap. So yeah, we just put the node in the smart pointer, and obviously now we create a new new tail, but we want to set the old tail next. And to do that, we borrow mutable. This is the intermutability stuff I was talking about. So now we can actually edit what's inside the reference counter pointer reference. I don't know. And so we can set the next to the clone, of the tail. So we copy, the reference of this inside the next. So the old tail has the next to the new tail. And then the new tail obviously should be set to the new tail. So that's how you do kind of the push. Now, it's kind of complex if you don't know what Rust is, but once you know Rust, it's pretty simple. Like, Rust is an easy language. If you're not trying to fight the bar checker, but let it help you. So now we want to print all. Classical print all makes a return. And we get the current node, which obviously we want to clone this, which will not just clone the option, but will clone or copy the reference count, so we have another reference to it. And you always want to, you cannot, have a, if you want to modify something, you can have a reference. You need to clone it, obviously, because otherwise, that data could die, and then you have a dangling reference. All right, so none. Then there's nothing to print. We break sum. Get the node. That's the sum, and we want to print the value. And to get, we want to just borrow, not mutably, but just normal, immutable borrow, to print the value. Why am I getting errors? Comma. missed a comma. And then current node will be the next node, so we have to borrow again, next again, clone again, because you cannot just get a reference without copying. Obviously that's how reference counting works. You don't want to cheat the system. System is there. Unreachable? Why is it unreachable? Wait, no, none. Why is it node? It's none. Alright, and we're finally done. Jeez, that's a lot of talking. And then if we run this, actually let me make sure we are using, nope, we're using the right one. And you get, your sweet, DoublyLinkedList. So here you go, 3 linked list implementation. And personally, if I was in the C land, I would love doing this, but Rust, since I'm on the Rust land, I'm going to be using Rust features because I want the memory safety and the lack of data race. So, and C is so horrible to do multi-threading. Rust is the future of programming, and I'm tired.